Sir, you have to start the recording also.
Hello, Suresh. Suresh. Suresh.
హలో మ్యూట్ లో ఉన్నారు అందరూ.
Sir,
Are
stream
you
is
ready?
starting, sir. Yes, sir.
లైవ్ స్ట్రీమ్ స్టార్ట్ అయిందన్న.
సురేష్
అన్నా
సార్ పంపించినావా?
వాళ్ళే పంపిస్తారు, నాకు తెలియదు ఏమి అవన్నీ.
సత్యనారాయణ సార్ రెడీ ఉన్నాడా? ఒక హాఫ్ అన్ అవర్ తర్వాత.
మేడమే తెలియాల, పద్మ మేడం.
సార్ రెడీ ఉన్నారు సార్, నేను అన్ని చూసుకున్నాను సార్.
ప్రిన్సిపల్ సార్ బిజీ ఉన్నాడు, ఒక 5 నిమిషాల్లో వచ్చి పండి సార్ అని చెప్పాను నేను.
ఓకే ఓకే
సార్ వస్తాడు. ఎంతమంది రిజిస్టర్ అయ్యారు?
900 అయ్యారు సార్, 900 అబౌవ్ అయ్యారు.
ఓకే.
Recording we can start, I think, sir.
సార్ ప్రిన్సిపల్ సార్ వస్తా అన్నారా సార్?
ఒక 5 నిమిషాలైనా రమ్మని చెప్పాను.
అదే
సురేష్ సార్, సురేష్ సార్,
చెప్పండి మేడం.
రికార్డింగ్ రిమైండ్ చేయమన్నారు సార్.
రికార్డింగ్ స్టార్ట్ చేద్దునా?
ఓకే సార్.
డిస్ప్లే చేయి. టైం ఉన్నాయి కదా, 10 కాలే. 11.
ఉంటా మేడం.
సార్
మీరు ఇన్వొకేషన్ టైంలో నాకు చెప్తారు కదా.
నేను ఎస్ సార్.
ఓకే, నో ఇష్యూ.
సార్ జాయిన్ అయ్యారా సార్? కాలేదు సార్. మీ హలో సార్.
రాజిరెడ్డి సార్ అన్మ్యూట్ చేసుకోండి మీరు. రాజిరెడ్డి సార్ అన్మ్యూట్ చేసుకోండి. అన్మ్యూట్ చేసుకోండి మీరు.
అన్మ్యూటే ఉన్నది కదా, ఇప్పుడు మ్యూట్లో ఉన్నా.
గుడ్ మార్నింగ్ సత్యనారాయణ సార్. సార్ వచ్చారు సార్.
సార్ గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్ సార్.
సార్ వినబడతలేదు.
సార్కి వినబడతలేదు.
మేడం ఒకసారి ఫోన్ చేయండి సార్.
ఆ,
సార్కి వినబడతలే. సార్ మ్యూట్ లో ఉన్నట్టుంది.
హలో.
అన్మ్యూట్ లో ఉన్నట్టు.
మేడం స్పీకర్ యాడ్ కాలేదు సార్ది.
కాలేదా? ఓకే.
ఓకే సురేష్ సార్, సార్ది స్పీకర్ యాడ్ కాలేదు.
సార్కి చెప్పండి మీరు.
ప్రిన్సిపాల్ సార్దా?
సురేష్ సార్, సత్యనారాయణ సార్ది కనెక్ట్ అవ్వలేదు ఇంకా.
స్పీకర్ యాడ్ కాలేదు మేడం, ఓన్లీ స్పీకర్ యాడ్ కావాలి.
అదే ఎలా యాడ్ అవుతుంది?
ఇప్పుడు వచ్చింది. ఓకే.
యా ఇప్పుడు ఓకే సార్, ఇప్పుడు యాడ్ అయింది చూడండి సార్.
గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్ సార్.
Hello.
Yes sir.
గుడ్ మార్నింగ్ సార్.
గుడ్ మార్నింగ్ సార్. గుడ్ మార్నింగ్.
Good morning.
Good morning,
Able to
sir.
listen me?
Yes.
Yes.
వినబడుతుంది సార్, వినబడుతుంది.
గుడ్ మార్నింగ్ సార్.
Good morning.
పద్మా మేడం, ప్రిన్సిపల్ సార్ వచ్చారా? ప్రిన్సిపల్ సార్
రాలేదు కదా సార్.
పార్టిసిపెంట్స్
సార్ ఇంకా రాలేదు. వచ్చారు సార్, వచ్చారు.
సార్ వచ్చేసారు. విల్ స్టార్ట్.
ఓకే మమత. So just to
audible ma'am? Am I audible?
Yeah, good morning all of you.
Good morning sir.
Good morning, sir. Good morning, sir.
Good morning, sir.
గుడ్ మార్నింగ్ సార్.
Good morning one and all. This is Dr. Mamta Thakur, Assistant Professor, Department of Mathematics, CBIT. On behalf of the department, it gives me immense pleasure to have the honor of welcoming you all to this one-day online webinar on the topic, A Popular Talk on Mathematics. I thank our management and the principal sir for providing us an opportunity to conduct this webinar. We shall begin this program with a prayer song. Suresh sir, can we play the invocation song?
I'm playing.
Sir, audio?
Madam.
Volume, please, sir.
तुषार हार धवला
Now I take great privilege in introducing our beloved principal, Professor P. Ravindra Reddy sir. Dr. P. Ravindra Reddy sir is a professor in the Department of Mechanical Engineering with 31 years of experience in teaching industrial and research areas. He has published more than 310 research papers in international journals and conferences. He has guided 22 PhDs and published 6 patents. He is recipient of many distinguished awards like UGC Fellowship Award, Engineer of the Year, Best Teacher Award, and many more. He has created an environment of innovation and entrepreneurship which has led to the setting up of a research lab at CBIT. Now, I request Professor P. Ravindra Reddy sir to address the participants. Thank you, sir.
Good morning, every one of you. Professor Raj Reddy garu, Professor Satyanarayana garu, colleagues, and the participants. I welcome you all this webinar and mathematics applications. I congratulate the department for organizing the series of webinars and workshops for the benefit of the participants. As we all know that the mathematics has got a major role in engineering and technology and everyone's life. So everywhere we use the mathematics. So how best you can see the application towards the meaningful way, and when you connect the relationship in engineering domains, I think that will make the participants so attractive, the mathematics, which we normally deal with just numbers and equations. But the reality of when we see the physical presence of various engineering domains, when we connect it, and really it's worth enough. I think the guest speaker today will deliver the content because of his vast experience, and all of you might get a lot of benefits, and you can have better interaction with experts like, so that we will have the futuristic way of learning that will be transformed to the students much better form. Once again, I congratulate the Department of Mathematics for organizing this webinar today till 1 o'clock. I enjoy the day and stay safe of the health is important. Another 2 to 3 months, we have to be very careful. I wish that every one of us will be more careful for COVID that is spreading in Hyderabad and also the rest of the country. Thank you all for giving this opportunity.
Yes, sir.
Thank you, sir, for your valuable and encouraging talk. Rajreddy sir, would you like to talk?
Yeah.
Should I continue? Yeah. Now
Respected.
I'll announce, sir. Now I request Professor P. Raj Reddy sir, Professor, Head, Department of Mathematics and advisor of today's session to address the gathering.
Respected Principal, Dr. P. Ravindra Reddy garu, CBIT, convener and co-convener of today online webinar, a popular talk on mathematics, Dr. A. Padma, convener, Dr. Mamta Thakur, co-convener, Dr. Sharada, co-convener. Good morning, one and all. A warm welcome to all of you. So about the Department of Mathematics currently has 12 faculty members who have vast research experience in various mathematics fields such as fluid mechanics, number theory, fixed point theory, operational research, and reliability. I am proud to say that 11 out of 12 faculty members are PhD holders, and remaining one faculty member pursuing his PhD in applied mathematics. So far, department has published 250 papers in various reputed journals at national and international level. Around 300 papers presented in various national and international conferences. Around 10 training programs were organized by Department of Mathematics. So recently in the month, this is the second webinar we are conducting, and one national seminar we conducted in the day July 7th. So we are one more webinar we are going to conduct in this month. So this is regarding this. Department of Mathematics. So I wholeheartedly thanks to principal because of his busy schedule. He came over and blessed the occasions. And also today's speaker, Dr. Satyanarayana sir, is a well-known mathematician. No need to introduce about him. Definitely, he will address the about the mathematics and its application for all audience. Thank you.
Thank you, sir, for a motivated talk. Now I request Dr. A. Padma, convener of this webinar, to speak few words. Over to you, ma'am.
Thank you. Good morning, one and all. Welcome to One Day National Webinar, a popular talk on mathematics. I am very much thankful to our Honorable Principal, Professor Ravinder Reddy sir, for his inaugural address. I am also thankful to our HOD, Professor Raja Reddy sir, for his motivational words. My thanks to the coordinator, co-convener, Dr. Mamata Thakur, and students, Mohammad Firasat Hussain and Nipuna, for their support in organizing the webinar. I extend my sincere thanks to Dr. Suresh, Professor Ganeshwar Rao sir, and all other my colleagues for their support in this webinar. And I thanks to all the participants. Also, as I am a convener of this webinar, I am happy to share the information related to today's webinar. Almost 900 participants have registered from various parts of country. The main objective of this webinar is to develop mathematical curiosity and use inductive and deductive reasoning. Before I invite our speaker, Professor K. Satyanarayana Garu, to deliver the speak, I would like to introduce Sir to you. Professor Satyanarayana Garu is retired professor of mathematics, Osmania University. Sir served Osmania University for 35 long years from 1974 to 2009. He was former HOD, head of the Department of Mathematics, Osmania University, and former chairman BOS in mathematics, Osmania University. Sir was also former chairman BOS in computer science and a faculty of science, Osmania University. Sir guided 4 PhD and 10 MPhil scholars and published 20 research papers in journals of international repute in algebra and its applications to finite geometries. He was also served Rajiv Gandhi University of Knowledge Technologies as visiting professor of mathematics from 2009 to 2014. Sir served CVR College of Engineering as professor of mathematics from 2014 to 2019 July. Sir's passion is teaching, delivering talks, and inspiring young brains. I'm really thankful to Professor Satyanarayana sir for accepting our invitation to be here with us today to share his experience-based advice on mathematics. Let us now welcome Professor Satyanarayana sir to deliver the talk. Over to you, sir.
So good morning to all of you. And I'm very happy to deliver a lecture. And when Padma Reddy called me and asked me for a title, I've tentatively given as a popular talk on mathematics. But what is that talk I have not divulged. But anyway, I'm here to divulge those things. Without wasting the time, let's get into the lecture. So, is my desktop appearing?
Yes, sir.
Yes, sir.
Okay. So, Vasya, are you ready? Yes.
Yes.
The stage is set and we are ready. And this is a webinar at CBIT today. And the title of the talk is Mathematical Modeling and Radiocarbon Dating by me. And I have combined the two ideas. One is what is modeling and some examples of modeling. And I combined with a radiocarbon dating, which is a technique, to find out the age of, objects, fossils, dead bodies, or even the trees, so on and so forth. So these two ideas we have, and this is a very, very basic lecture. Those of you who are thinking mathematical modeling means I'm going to talk about big modeling, it is not. It is my audience, my group of audience is some of the engineering students and the young faculty and the maths enthusiasts. So this is my target group. It's not for, I'm not going to talk anything related to research or anything like that. It's a popular talk. Popular means it will have all ingredients, namely it will have an excitement, it will have information, and by that, we'll also derive some enjoyment. So let's get into that.
Yes.
So this is the mathematical modeling and radiocarbon dating. It is me, Professor Satyanarayana from Usmania University, retired from the great university. I worked with Rajiv Gandhi University for Knowledge Technology and Severe College of Engineering as Professor of Mathematics. Agreed. Now I will acknowledge, before that, let me first of all thank the CBIT and the principal, Professor Ravindra Reddy Garu. I also thank my esteemed colleagues in the Department of Mathematics, Dr. Padma Reddy, Dr. Mamta Thakur, Dr. Sharada, Professor Raji Reddy, Professor Ganesh Rao, and others for extending the invitation. Agreed. I acknowledge, this is my acknowledgement. I acknowledge this book, Erwin Krzyk, Advanced Engineering Mathematics, 10th edition. The lecture is drawn inspiration from the first few pages, namely 15 or 20 pages. From that, the lecture is made. And some of the Google images I have used. I acknowledge all of them. Agreed. What is a mathematical model? First of all, we have a problem. It may be a physical problem or an engineering problem or some such thing. So we take that problem, make mathematical formulations. That means we write equations in terms of functions, etc., etc. So we'll convert that problem into a mathematical formulation, and that is called a model or a mathematical model. To solve a problem of physical nature, we have to formulate the problem as a mathematical expression or expressions in terms of variables, functions, equations, etc. Such an expression or expressions is known as a mathematical model of the given problem. Right. So if you have the mathematical model for the problem, then we'll have the process of setting up a model for the physical problem. That is the first step. Once you get the mathematical formulation, what do? We solve it mathematically, and then we interpret the solution in physical or other terms. And this entire process of these steps is called the mathematical modeling, or briefly modeling. And in your Kresik's book, this is the very first page. Very first page. That means his idea is that you teach mathematics like this. That is, we are teaching engineering mathematics. That means we are going to have a modeling only. So it means all your problems are to be done modeling only. What are we doing? We are setting up a problem mathematically and we are solving and we are keeping quiet. That's the problem. So you have to interpret. Now you have to check whether your model is correct or not, and so on and so forth. Let's see the flow chart, what I have said now. First, we have the physical problem. Next, we have the physical laws and then convert into mathematical equations. Then we have the mathematical model. Then we solve. Then we get a mathematical solution. So how do you solve? We will solve analytically if you are capable of doing it. Otherwise, use a MATLAB. Otherwise, a Mathematica or a Maple. If it is a fluid dynamics problem, use some numerical techniques, difference methods, finite element method, finite volume method, whatever you want, you solve it. That is your problem. Then after getting the solution, you interpret. And if your interpretation is close to the reality, then you accept the model. If your interpretation is far away from the reality, then your model is not accurate. Then what do? You will modify the hypothesis. That means you will modify the hypothesis. You got a different problem. Start from the physical problem and then go on doing all these steps. So you continue, go above to the physical problem, go on doing it until you get a model which is acceptable to you. Once it is acceptable, then you make recommendations. For example, today you have the COVID-19, make a mathematical model and solve the equations. And if your model is coming close to the reality, you accept it. And if you once you accept, you will send the recommendations to the government. Yeah, so that means mathematical modeling. And if you see today's scenario, mathematical modeling is very heavily used for COVID-19. And go to Google and search COVID-19 and mathematical modeling, you will get thousands of papers. Agreed. So some of the models, what are the models? They can be a system of differential equations, what we use in population control, or a probabilistic model, which is used in a risk management, or a linear programming model, or a problem minimizing the environmental damage due to pollutants. So like this, some of these are the models and many others. So this lecture is related to something related to engineering, science, and technology. So the typical mathematical modeling techniques for engineering include computer-aided design, finite element modeling and analysis, and CFD, computational fluid dynamics. Many of you are working, in fact, on computational fluid dynamics. What are the uses of mathematical modeling? So mathematical modeling solves the real world problems, and it is widely used today because we have the computation power, more computational power. That is, the increasing computational power is there. And we have the computing, so many computing methods. That means we have got supercomputers and thereby we got an increasing computation power. And the computational methods, that is the numerical methods, are also increasing. So because of that, it is gaining a lot of importance. And it is used to handle large scale and complicated problems. It's not for small problems. You know, suppose you want to have a weather forecasting, you can make a mathematical modeling. It is a large scale and which will depend upon many parameters, and it will be which will be a very complicated problem. So the following are some of the areas where modeling is used: space technology, aerospace science, climate modeling, combat and war related problems. This is related to defense, population dynamics, water resources, drug design, material research, manufacturing and design, seismology, a very important area, economics, environment, medicine, and biology, etc. Biology, mathematics in biology? Yes, there is a subject called mathematical biology today, which is gaining a lot of importance. So in many cases, our model is a differential equation. We know, we study differential equations, we teach differential equations, so on and so forth. I will throw some light on differential equations. Many physical concepts such as velocity and acceleration. Velocity is ds by dt, and acceleration d square s by dt square. They are all derivatives, first derivative, second derivatives. Therefore, model is often an equation containing the derivatives of an unknown function. Such a model is a differential equation. And once we have the differential equation, what do? We solve. That means we will find a function which satisfies the differential equation and study its properties, graph it, find the values of it, interpret in physical terms, so that we can understand the behavior of the physical system in our given problem. And this model and the differential equations are widely applied in many branches. Differential equations are used to model physical systems that arise in science and engineering, like models which describe heat transfer. Fluid dynamics people will do. Heat transfer is in mechanical engineering. Chemical engineering processes is a chemical engineering, chemical technology. Electronic circuits with time-dependent currents and voltages, EC people will do that. Real-world problems involving fluid dynamics, which civil engineers will do. Control mechanisms in biological systems, biologists will do. Engineering systems, any engineer will do. The dynamics of socio-economic structure is a socio-economic structure. It's in sociology, economics, the dynamics of that. They use differential equations. Activities of a biological neuron, the study of the neuron. And today there is a big subject what is going on called brain modeling. And systems such as robot control in robotics, where differential equations are very heavily used, automatic process control, so on and so forth. So you have to convince your students that differential equations have a lot of applications, good many applications like this. And these are all engineering items. That is why maths is a very essential course. And we need the service of mathematics teachers. So these are some of the, there is a deadline, there is a, already I have acknowledged Erwin Krzik, Advanced Engineering Mathematics 10th edition. These are the, to convince my audience, these are the, images that I brought from Krzyk's book, where we use first order differential equations as the models. The first one is the freely falling bodies. From a tower, this is a freely falling body, and y is the height of it. Then you get second order differential equation. Y double prime is equal to g, where g is the constant. That is g is this, and the second one is parachutist, the parachute, and where we are calculating the velocity v, where it is a first order differential equation, but there is a v square term, which will make it is a nonlinear differential equation. And all these equations, in some way, some manner or the other, we will solve in the class. It is the flowing of the outflowing the water from a jar, where we are calculating water level h, which will be decreasing, and that is modeled as h prime is equal to minus k times root h. And we also have the second order differential equations as models. The first one is this vibrating mass on a spring. There is a spring, and to that there is a mass attached. There is a ball attached to it, and we give a push to it. It vibrates on a spring, and where we get a second order differential equation. So why do we study differential equations of higher order? So one of the reasons is second order differential equation find applications like this. And beats of a vibrating system, where you use y double dash plus w naught square y is equal to cos omega t. This is precisely the equation what you solve in your class with a initial value problem. And we also have, this is easy people, we have a RLC circuit, and where we calculate the current I in an RLC circuit. This is the RLC circuit, where we get a second order differential equation. Second order differential equation. If L is not present, you have a different models also. You have the simple harmonic motion. This is the pendulum, and this is the second order differential equation which we will solve. So all these are the things in some form or the other we solve in the class. What is missing in our teaching is that this models we are missing. So if you can spare some time and explain these things with the physical problem. With the physical problem, that first step you formulate, that is make a modeling, then you solve the differential equations. That will be interesting. Not only that, the student will understand the importance of mathematics. And the higher order differential equations are also used. Is in the case of the bending of the beams, that is the deformation of a beam, where there is a pressure applied. Is a beam, is a bridges people construct, where there is a lot of load that is having, and the pressure will be there, and a fourth order differential equation, you get it. So there is a need to talk about the differential equations of higher order also. And there is also a need, there is a model which is called the prey and predatory models. This is the gaining lot of importance today. A lot of researchers are also doing. This is the one, Lotka-Volterra predator prey model, where in this model, one is a prey, these are the preys, these are the predators. These are the predators. They eat these things. And what happens as time passes, if this population increases and this population will become extinct, then there will be an ecological imbalance. So Y1, Y2, Y1 related to this, Y2 related to this, and this is two people, Lotka-Volterra. Lotka is a mathematician, physical chemist, statistician, and he is famous for his work in population dynamics. And Volterra is an Italian mathematician, physicist, known for his contribution to mathematical biology. Look where the maths is going on. Math is going into the population dynamics, math is going into biology, and so on and so forth. And this kind of study is very, very important. And it will tell you what happens to our environment. So this will be a very interesting model. So that is the end of some of the models which are very familiar to us. Now I will go to the exponential model, which we teach in our class. In 1798, Malthus is not a mathematician, is an economist in the field of demography. Demography is a subject of which talks about the life and death of populations. He proposed a mathematical model for the population growth. Look at a mathematician. He is not a mathematician. He is an economist working in the demography, and he has given this model, the Malthus. What is that he has given? So he proposed by the assumption that the population grows at a rate proportional to the size of the population. That is, dp by dt, the rate of population, is directly proportional to the population. Now, when this is possible, that means, if you give a model like this, the model will give you the population will be enormously, enormously increasing, exponentially increases. So if the population exponentially increases, what happens? There will not be any place to live in for other species. But anyway, this is a reasonable assumption for a population of a bacteria or animal under ideal conditions. He has taken the ideal conditions. Ideal conditions means what? There is a lot of immunity. There are no deaths. A lot of food is available. Environment friendly, and so on and so forth. That means unlimited environment. You can live, and you are the only species. Adequate nutrition, lot of food. Absence of predators. That means nobody will kill you. And immunity from diseases. That means you are so immune, no disease will make any harm to you. That means your death is not, there is no death for you. That is why the exponential it grows. I'll ask a question. Suppose we take this model for the human population, is it realistic? So it's very unrealistic. That we will discuss at the end of the next slide. So model, we have a solution, and we will make an interpretation. dp by dt is directly proportional to p. Therefore, dp by dt is equal to beta p, where beta is the constant of proportionality with the initial condition p at t naught is equal to p naught. So this is the initial value problem. So what do? Variable separables. Variables are separated and integrated from time t naught to t. So integrate dp by p beta time beta dt from t naught to t, from p naught to pt. So what will be the integral of dp by p? ln p, log p from p naught to pt. So that will be log of pt minus log of p naught, and this is beta t from t is equal to 0 to t. That is beta t. And this left hand side, log of pt minus log of p naught, will be log of pt by p naught. Yes, pt by p naught, that's equal to beta t. And we will remove the logarithm. So if you remove the logarithm, pt by p naught is equal to e power beta t. Therefore, P of t is equal to P naught times e power beta t. What happens? What happens? As t tends to infinity, P of t tends to infinity. So that means the population grows exponentially. And look at the growth, exponential growth. In our subject, while teaching to the students also, many times we don't show the curves. But if you can show the curves, then they will understand better. That means your population is growing enormously. And in this model, the population grows exponentially. This may be true for bacteria or virus or something like that. But you see, there is a retarding situation also. There is a remedy for that. There is a medicine for that will retard, and thereby the exponential growth may be decayed. So this is in reality, this model is very unrealistic because environments impose limitations to population growth. There are a lot of limitations to the population growth. So this may be true for other models, but not the human population. But you know, because this model, I cannot take it for the modeling the human population. I will revise it, and we have done it. There is a statistician, Belgium statistician, who has given a logistic growth model. This is a revision of the exponential model what I was talking about. A Belgian statistician, Verhulst, showed that the population grows not only population growth not only depends on the population size, but on how far the size is from its upper limit. The upper limit is M, called its carrying capacity. That is, it is a maximum supportable population. That means the assumption is your population will not increase beyond M. Why? Because of the environmental restrictions, because of the food availability, because of several others, because of the deaths, so on and so forth. So that means your population, the growth rate depends on not only population, as Malthus said, but will also depend on this M minus P. M minus P is, that is lag. That is, M is the maximum supportable population. M minus P is the thing. That means some deaths takes place. So therefore, not only P, but also M minus P. So Verhulst modified Malthus model is to make the population growth proportional to both the population P and the new term M minus P. So you got the differential equation now. That is the logistic equation. So this is the differential equation dp by dt, that is the growth rate, is proportional to P and M minus P. So P into M minus P, proportion of constant is K. This is the equation 1. So is known as the logistic equation of Verhulst, or sometimes called Verhulst equation. And the logistic equation is often used to model a population that inhabits an environment with carrying capacity M, where M is the maximum population that this environment can sustain on long-term basis in terms of the maximum availability of food, for example, so on and so forth, availability of medicines, and so on. So this is a very important equation, and actually I wanted to solve and interpret, but that becomes more mathematics, therefore I did not make it. You can see it, this one, in your Krezik's book. This equation plays an important role in population dynamics. There is a subject called population dynamics. It is a field that models the evolution of population of plants, animals, or humans over time T. look at the comparison of exponential growth. This is the exponential growth curve. The largest growth curve. That means this will not go beyond m. This is the m carrying capacity. It will not grow beyond m. It will be like this. Even it may come down also after some time, if for some reasons, environmental reasons or food reasons, something like that. Or if it is favorable conditions, it can go up to m only, but will not grow beyond that because of the restrictions. So that's a very realistic one. So your population, if you see human population, so there is a carrying capacity for the entire world, and it will not grow beyond that. So we will stop that discussion there. We will now go into mathematical modeling. Your first step is formulation of the problem, that is the mathematical model. Second step is your solution. Third step is your interpretation. Finally, fourth step is we make a decision that may be of an industrial nature or recommendation to the government on a public policy. So that's the steps that are involved for mathematical modeling. I will take an example what we do in our BTech first year, that is the exponential decay. And then my story I will connect to what is called radiocarbon dating, and I will talk on radiocarbon dating related to mathematics. So we have a physical problem. So given an amount of a radioactive substance, say 0.5 grams, find the amount present at any time t. This is your problem. So what's the physical information? Experiments show that at each instant, a radioactive substance decomposes or decays at a rate proportional to the amount of the substance present. This is an experimental evidence. So take that, then write the mathematical equation. Step 1, you set up the model for that physical problem. So what is that? Denote the amount of the substance as y of t at the time t. By the physical law, dy by dt, that is the rate of change, is proportional to y. So therefore, dy by dt is proportional to y of t, and dy by dt is equal to minus ky, where k is a positive constant, is a constant of proportionality. Why the minus is coming? Minus is coming because there is a decay that is taking place. Minus k because y of t decreases with time t. And the value of k is known from experiments on the radioactive substances. In our solving problems, we are given some additional data to us, and thereby we will find out the value of k. Otherwise, they will find in a laboratory. Step 1. Step mathematical model. Y of t is equal to 0.5 when t is equal to 0. That's the initial value. Y naught is equal to 0.5. Y naught is y at 0 when time t is 0. The model of the problem is this. This is the big dy by dt is equal to minus ky, k greater than 0, y at 0, that means y naught is 0.5. That is this is a first order initial value problem. So why initial value problems come, you can say like this also. So we want to solve this initial value problem. Take it. Step 2. dy by dt is equal to minus ky. variable separables, integrate, then you get integral of 1 by y dy is equal to minus k integral dt plus c. Or ln y is equal to minus kt plus c. Remove the logarithm. Y of t is equal to c into e to the power of minus kt. To find the value of c, we'll use the initial condition. So y of t, that is y naught is equal to 0.5 when t is equal to 0. Using this, we get c is equal to 0.5. That is y of t is equal to the initial amount y naught into e to the power of minus kt. And thus we get a particular solution. Y of t is equal to 0.5 times e power minus kt. So this is your step 2. Step 3, you will interpret this result. So it starts from the initial amount and decreases with time t. As t tends to infinity, it will tend to 0. As t tends to infinity, it will tend to 0. So how the graph will look like. In this graph, as Krasik has taken, k is considered as 1.5 as an example, and this is the 0.5 initially, and decreases, and at infinity, as t tends to infinity, it will become 0. Using this, you can calculate the half-life period, so on and so forth. So many ideas you can have. Agreed. Now what it says is, I am changing my scenario. That is about that. Now I talk about radiocarbon dating. So I am going to combine these two ideas. Radiocarbon dating is something related to chemistry, and with the mathematical modeling I will be doing. It is a method of determining the age of an object containing organic material by using the properties of radiocarbon, which is a radioactive isotope of the carbon. So any object which is containing organic material, you can find out its age. For example, you have a log of wood, very old one. We want to know what is the age of that. You can use radiocarbon dating, because as time passes, that wood will decay and go on becoming into a carbon, and it will be transcending from radiocarbon to ordinary carbon. Right. Who have done it? This is Willard Libby, who is a physical chemist, was an American physical chemist, noted for his role in the development of radiocarbon dating. It is a process which revolutionized archaeology and paleontology. So for this work, he got a Nobel Prize. Radiocarbon dating was developed in the late 1940s by Libby, who received the Nobel Prize for this work in 1960. This is the great Nobel medal. And the citation is for his method to use carbon-14 for age determination in archaeology, geology, geophysics, and other branches of science. And the Nobel Prize was given in 1960. So, OHG. So what are you saying? That is on the Alps mountains. The ice was there, and there was one mummy they have found out. They wanted to know when this man was dead, or what is the age. Age means, age doesn't mean that that is real age. So very long before he might have died. And what is the time? In September 1991, the famous Iceman OHG, he is called as OHG, a mummy from Neolithic period of Stone Age found in the ice of Orgel Alps. Alps is mountains. Orgel Alps, full of snow, and they found a mummy there, and it belongs to the Neolithic period. And they named that mummy as Voyage because it was found at Voyagel Alps. So these are the people who have found this mummy here on the Voyagel Alps, called as Voyage. And what is the question now? The question now is the age. The question: when did Voyage approximately live and die? If the ratio of radioactive carbon 6C14, that is is a radio one, to ordinary carbon 6C12. Ordinary carbon is 6C12. 6C14 is radiocarbon, and the ratio of 6C14 to 6C12 in this mummy they have found 52.5. This is a very vital information what they have found, and using this they have found the age of that mummy. Let's get the strength of mathematics. The physical information in the atmosphere and in living organisms, the ratio of 6C14 to 6C12 is always constant. In our case, it is 52.5%. We can estimate the age of the fossil by comparing radioactive carbon ratio in the fossil with that in the atmosphere. That ratio is very vital for us. Let's get into mathematics. The modeling. This is given by this. We have already seen. And on solving, we got this. And using the initial value, we got this. Y at t is equal to y naught into e to the power of minus kt. We have the half-life of 6C14. Half-life means the time that is required to decay to the half of the original amount. So yt will be y naught by 2 when t is 5,715 years. That is yt is y naught by 2, y naught into e to the power of minus k times t. T is the half-life h. Agreed? Y naught cancels, and e to the power of minus kh is 1 by 2, that is 0.5. Take the logarithms on both sides. Minus kh is equal to ln of 0.5. K is equal to minus ln of 0.5 by h. And that is equal to minus ln of 0.5 by h is 5,715 years. And this is 0.301212, so on and so forth. And our student will ask the question, sir, here is a minus, here is a minus. How come this is plus? This is because ln of 0.5 is minus. See, ln from 0 to 1, they takes minus negative values. And that is why this constant. So the constant is required for us. So now let's get into solution. We use the ratio 52.5% to find t when Voyage died. By research, it was found he was actually killed. Now y is equal to y naught e to the power of minus kt. And y by y naught, that is the ratio. The ratio is 52.5%. So e to the power of minus kt is 0.525. Take the logarithms. Minus kt is equal to ln of 0.525. And t is equal to ln of 0.5 by minus k. Minus k is a positive value, minus is there. Ln of 0.525 is a negative value. And when you substitute, you'll get 5,312 years approximately. So what is that? Our question is, Voyager was dead, actually killed about 5,300 years ago. So look at the power of mathematics, the modeling, and the power of, say, radio carbon dating. And so therefore it's an interdisciplinary situation. So if you teach like this, your student may be very much interested, and it will be an interesting thing. So therefore I have done my modeling, several examples. Then I brought my decay problem. Then I connected to what is called the radiocarbon dating, and I have solved the question. So that's the one. Yes, again it says I want to change my topic. That means I'll use my radiocarbon dating, and I want to find when zero, our great zero, was invented. It is known zero was invented by an unknown Indian, and by inscriptions on some temples, zero was there. Those temples were built somewhere 8th or 9th century. They thought the zero might have invented somewhere in 9th century or 8th century, like that. People thought for a very long time. But the radiocarbon dating tells us that is wrong. It's actually 500 years before that 9th century. Somewhere at the 4th or 3rd century itself, the zero was invented in India, and it was heavily used by the rishis, sages, and so on and so forth. So let's talk about that. Radiocarbon dating and zero. Zero. In the ancient Indian system, the value of nothing was represented by a small dot. This symbol appeared inscriptions on the wall of Chaturbhaja temple, Gwalior. Gwalior is in Madhya Pradesh in India. This symbol appeared in inscriptions on the Chaturbhaja temple, Gwalior in Madhya Pradesh. This is the inscription. And where the zero is there, this is the zero. This is the zero which is appearing there. And when this Chaturbhaja temple is built, and because of that, this is the first time when they have noticed this zero. They thought maybe somebody might have invented, maybe at that time. So the temple dates back to the 9th century, and earlier studies of the manuscript have estimated its age at anywhere between 8th and 12th century, because carbon dating was not there in those days. So because of this temple was built somewhere in 8th to 12th century. So somewhere in the 9th, it dates back to somewhere in 9th century. This was the estimate what people thought for a very long time. But very recently, it is found it's not 9th century. It is something like 4th century. They have used carbon dating. How? To use the carbon dating, there must be something, you know, like in our case, Talapatra Gandha, in Telugu, what you say. But in those days, Talapatra Gandha was not there. They used to write on the bark of a tree. Agreed? So they have found a manuscript called, today called Bakshali manuscript. It's particularly I brought because, you know, all our teachers and young teachers and young students must know the history of Jiro. Bakshali manuscript is an ancient Indian mathematical text written on birch bark. What is birch bark? The strong and water resistant cardboard like bark from the birch tree. It was found, actually was unearthed from the field of a peasant in 1881 in the village Bakshali, Mardan, in the United India, near Peshawar, in the present day of Pakistan, in the United India. By Indian only, not by Pakistanis. Agreed. So they have found this manuscript and it is written on the birch bark. Now what happens to birch bark? Birch bark will be dying, decaying. When it is decaying, it consists of organic material, and it will be dying. So that means that radiocarbon will be converting into carbon. So that process will be there. And therefore, there is a method, there is a technique of finding the age by radiocarbon. So there is a big laboratory in the Cambridge University, and they have found. So this is the Bakshali manuscript. This is a one-page Bakshali manuscript where zero was there. The reading from right to left, the small dot zero is the seventh character at the bottom of the manuscript. This is the one, and I will magnify that. Yes, this is the one. So this is the one that is there, and they have taken this manuscript, and the Indologists have taken this manuscript. They wanted to study, but they could not. They left this manuscript consisting of 73 pages in Cambridge Library. It was dying there. It is dying there. Very recently, they have picked up and they have found out what is the age of this manuscript using carbon dating. So this is the one. The manuscript contains the earliest known Indian use of a zero symbol. It is written in Sanskrit with significant influence of local dialects. So these are the numbers. These are our present numbers. These are the numbers what they have used. And the manuscript was acquired by Indologist Rodolphe, who presented it to the Oxford libraries, Bodleian libraries in 1902. Afterwards, he has not shown any interest on it. From 1902, it was lying in the darkness in in that Oxford libraries. Very recently, so they have taken that manuscript. The Oxford scientists conducted carbon dating on this Bakshali manuscript. So this is the Oxford laboratory, you know, finding carbon dating. This is all the equipment. To their surprise, the text was far older than they had expected. A solid 500 years older, in fact, dating back around 3rd or 4th century. So it's not the 9th century. It is the somewhere is the 4th and the 3rd or 4th century. So therefore, that gives it quite the lead over the temple. On the temple, but because of the temple, we thought it is the 9th century. And we thought it was first written instance of the manuscript on the temple, but it is actually, it's not the 9th century, but it's actually 4th century. So Brahmagupta, you see, I will give an instance. It was only in India that this zero developed into a number in its own right. When? Between 597 to 668. That means their dating 4th century is right. After 4th century, Brahmagupta studied this zero. And Brahmagupta, an Indian astronomer, wrote a text called this one. This is a Siddhanta, Brahmashputi Siddhanta, in the 6th century, which is the first document to discuss zero as a number. If you want to believe this, it is somewhere at 6th century. But it is not 6th century, it's the 4th century. So that is the one. And an appreciation has come from the professors from the Oxford University. Marcus, a professor of mathematics at the University of Oxford, he said, we now know that it was as early as the 3rd century, the mathematicians in India planted the seed of the idea that would later become so fundamental in the modern world. The findings show how vibrant mathematicians have been in the Indian subcontinent for centuries. So look at our mathematicians, what they have done. Some excellent work finding the zero. We have not, whereas we have not recognized them, but the Oxford University people, they have found out, and they brought that manuscript and they said an unknown Indian, that's a very sorry state of affairs, an unknown Indian found this somewhere in the 4th century. That is the story of zero and radiocarbon dating. Because I'm talking about radio, I'm interested in zero, I brought the zero. So that's the story. The story has almost come to an end. Glorious heritage. India's contribution to mathematics, astronomy, science, medicine, and a variety of other fields has been very significant and invaluable. See, we want to tell our students that our Indians have done some excellent work. And we Indians should be proud of our glorious heritage. Pat your back. So because you are an Indian. So that's the end of the story. And that's the story of mathematical modeling and radiocarbon dating. Cheer up. This is my trademark. Well, normally at the end, I will give some good slogan, something like that. Cheer up. Here is a quotation. We owe a lot to the Indians who taught us how to count, without which no worthwhile scientific discovery could have been made. Not only zero was invented by Indians, the process of counting was also given by Indians. And that's what this great man says. You cheer up. We owe a lot to the Indians who taught us how to count, without which no worthwhile scientific discovery could have been made. Who said this? Albert Einstein. He's a great physicist who is a great admirer of mathematics. Agreed. Maybe there is one more great saying. It is particularly very important to all our young friends and student community. Normally, people will get depressed whenever we face failures. See, for those people, I will not say I failed 1,000 times. I will say that I discovered there are 1,000 ways that can cause a failure. This is Thomas Edison. And normally I make it end with a smile. That means the teacher should do these things in your class whenever you're teaching. If the students are get bored, crack a joke, but don't crack jokes which are very nasty, which are which are related to mathematics. If you can crack a joke, it's very difficult. Then the student will be get elated. And here is this one. This is taken from Google Images. A square plus b square is equal to c square. Who said this? Pythagoras. E is equal to mc square. Who said this? Einstein. C square has gone. And these two people, what are they doing? Let us see. Let's see. They are fighting. C square is mine. What says Pythagoras? C square is mine. What says is Einstein. And our emoji laughs with his full heart. So that's you end with your lecture with a smile. I hope that I brought some of the fundamental ideas of modeling. I brought some of the examples, and I have introduced and explained to you what is the radiocarbon dating and how it was used for exponential decay problem of the OHG, which is a mummy there. Then this carbon dating, how it was used to find, when zero was found. That is, zero was found. Now you have to say 4th century, not the 9th century, not the 6th century. So that's the outcome of this result. If that is the case, I hope I have made you to understand, and I made you to enlighten. I made you to enjoy the lecture, and I am sure you might have enjoyed the lecture. If it is so, I'm signing off. If it is so, send your feedback. Feedback means, not the feedback of the webinar, but to send the feedback of the lecture to my telephone number through WhatsApp 94901 Thank you very much. I thank the organizers for giving me an opportunity to talk in this webinar, so that I will share my ideas with all my young friends. Thank you very much.
Sir.
So one minute, sir. On behalf of the Department of Mathematics, wholeheartedly we are thankful to you, sir. You delivered wonderful lecture on first order differential equations, then its applications, carbon dating and zero and about zero. Very wonderful lecture, sir. Informative and knowledgeable and thought-provoking lecture, sir. All we are very thankful to you, sir, on behalf of the department, sir.
Thank you.
Sir, there are few questions from participants, sir.
Yes.
Can you brief? Yeah, one question from participant. Can you brief more about brain modeling and its few real life examples?
Oh, very difficult. It's very difficult. It's a very advanced subject, and it's very advanced subject. I'm sorry, I am not a PhD in modeling. I am a PhD in algebra and its applications. And brain modeling is considered to be one of the latest topic. This I was browsing through so many, texts. And brain modeling is a very one. It is there in a neuroscience also nowadays. In the neuroscience, the people are talking about the brain modeling, and that brain modeling they will bring very close to the computers as well. So that's the context.
Yeah. Sir, next question, sir. Can you please discuss Duhamel principle and its application in engineering?
Which one?
Duhamel principles. DHUAMELS.
No, I'm sorry. I do not know what is that Duhamel.
And another
if
question.
That is the case, I will note down, and if there is any opportunity, I will explain in the next webinar.
Okay, sir. So, another question from the participant. Can we give a mathematical model to reduce COVID faster? Why, sir?
Yeah. Yeah, it's a COVID modeling. Go there and Google it. COVID modeling is there. Maybe in your webinar, I don't know in which webinar our professor
Gopal sir.
not Gopal, Krishna Reddy sir is going to talk about modeling of course, statistical in a statistical way. In a statistical way, he wants to discuss COVID-19. COVID-19, maybe thousands of articles are coming, but which is the realistic model? Still, people did not find. And that all the outcomes, what is that? Frequently washing, 6 feet to that, and all those things are evolved through modeling. There is an article which is appearing there. Yeah.
Sir, another question, sir. Can we visualize natural cataclysm using mathematical modeling?
What is cataclysm?
Cataclysm means, I think it is, this is something
Maybe the man who is asking,
violently
okay,
destructive.
some of the student or teacher who is asking, maybe more knowledgeable. So we don't know about that, right?
Okay, sir, these are the questions. Is there any one other question? Scope of research?
Well, a lot of research, everybody is doing. Fluid dynamics people are doing only these problems. Fluid dynamics people are only doing this problem. And all people, whoever is doing modeling is a lot of scope is there. See, lot of models are coming. The predatory prey model, so on and so forth. So a lot of modeling. See, I think half of the PhDs, maybe more than half, are coming from modeling only.
Yeah.
But they may not be telling us what is modeling. They take a situation, they model it, solve it, use some finite difference method, that method, this method, and then go on doing the curves, what are curves, their graphs, and then interpretations. A lot of things are going. Rajreddy may be knowing is also a fluid dynamics man.
Yes.
Sir, I have one doubt, sir. This regarding carbon dating, sir. Sir, patents will different people invented and a court law they are filing the cases in court who invented that. Then afterwards that patents question will come, sir. By using this radiocarbon dating, can we easily find out that is, sir, who invented first, who invented not first? That is.
There is a Libby, that man only Libby.
Yes.
Libby is the man, and there is a patent already with him.
Sir, అంటే అది ప్రొసీజర్ తోటి మనం కనుక్కోవచ్చు కదా సార్ ఈజీగా అది దట్ ఈస్ ఐ మీన్
No, we may not find what is called that patent when it is patented and all that, but it is there should be an organic material.
Yes, yes.
Carbon dating means what? Radiocarbon dating means what? There must be an organic material must be there. Why organic material is there? Organic materials will decay into the ordinary coal, that is ordinary carbon.
Yes,
in that process they will come like this.
Okay.
From 6C14 to 6C12. That is the change it takes place. And then what is the ratio that is present? And then what is its half-life? So for example, you take a log of wood, maybe a very old one, what we find in maths department. Let's say in maths departments there is one chair. That chair was, people used to say, that belongs to the Nizam era.
Yes, sir.
Nizam era. Even as head of the department, I was also lying down on that chair. And they used to say that is Nizam's chair. Nizam's period, that chair was there. Suppose we want to know,
Yes, sir.
what is the age of that.
Yes.
Then you can do that. But even then, that wood should decay. That means it should get into that carbon stage. That means now it may not be possible. Maybe after 1,000 years, it will get into the wood form, the coal form or carbon form. Then you can find out. So that you can do. So like that,
Thank you, sir. Thank you.
right. Thank you very much. I thank Professor Raj Reddy and Professor Ganesh Rao and others, Dr. Padma Reddy in particular, Mamata Thakur and Sarada for inviting me and asking me to give a lecture. Thank you very much, and we will meet at some other time at some other
Yes, sir.
event.
We'll meet
Thank you
you,
very
sir.
much.
Sir, it is a really wonderful session, sir. We are honored and delighted with your presence, sir. And now I request Dr. Mamta Tagore to do the valedictory. Over to you, madam.
Right.
Thank you, ma'am. Sir, today's session has given an enriching learning experience to all the participants. Your talk has given a new dimension to our knowledge of mathematics. We were introduced to different mathematic models and radiocarbon dating. You even made us understand applications of differential equations to various domains of engineering. We are all enlightened by your extempore talk. On behalf of Department of Mathematics, CBIT, and all the participants of this webinar, I thank you for such an excellent talk. I thank our HOD sir, Dr. P. Raj Reddy sir, for always being there to support and guide us. I thank Dr. A. Sandhya Reddy ma'am, HOD, Department of English, for always encouraging us. I thank all the colleagues and not the least, the student coordinators for extending their help in organizing this webinar. At the end, I thank all the participants who made this webinar a successful one by joining in huge numbers. Thank you one and all. Thank you, sir, for joining us and hope to hear you again in future.
Thank you. Thank you very much. Bye.
Thank you, sir.
Thank you, sir.
So, where are the organizers? Organizers, where are the organizers?
Good afternoon, Raj.
Organizers and colleagues.